First of all, thanks for the invitation. I'm quite excited to present and share, the latest iteration of the V-JEPA work. So my name is Nicolas Ballas. I'm a researcher at FAIR, based in Montreal. So I've been at FAIR for almost 8 years now, and working on self-supervised learning and how we can use self-supervised learning to build world model, which is kind of the topic of today's presentation. So yeah, I guess we can start. Cool.
Awesome.
So today, specifically, I will present our recent work, V-JEPA 2. So the title is Self-Supervised Video Model Enable Understanding, Prediction, and Planning. And you can see it's kind of a collaboration between quite few people. And really the goal of the project was to kind of demonstrate that we can use the self-supervised learning machinery to build a world model and kind of solve downstream planning tasks. Yeah, maybe before kind of describing the approach, I just want to motivate why planning in the physical world and world model are kind of an important problem. And for that, I have a kind of a small example, a motivating example. So, okay, so let me pause here for now. So here you see a COVID. This is like a small clip from a BBC documentary. And you can see here you have a bit of food in this tube, but the COVID is not able to reach it directly. So he has to find a solution in order to be able to get the food. And this is kind of a zero-shot problem, if you will, because it's like a new situation. Like he was not exposed to this type of problem before. And you can see he's kind of looking around. Then he's going to pick a rock, use the rock to kind of make the water go up. And all of a sudden, you're going to get there. He can reach the food, right? And I think this is an interesting example because many species have demonstrated the ability to plan and to some extent reason about problems that require common sense understanding. You need to understand what is the effect to put a rock into the water, and also like low level motor control. And the other interesting thing is he's not just trying random stuff. He kind of directly know what is a good solution and just tries a good solution to get to his goal. And how do we enable similar behavior in machine is kind of an open question. And so this is where like the coming the world model hypothesis. So if you look at literature of different domains, they all converge on this idea of the importance of world model. Sometimes it's also called like a mental model in psychology. And really, the goal of this type of model is to simulate, have some kind of inner simulator of the world and see how the world changes in response to agent action. So here I have like two kind of reference points. One is Nature of Explanation, which is kind of an old book from the 1934. And already he kind of developed this idea of, that organisms have a small scale model of external reality to kind of simulate what is the effect on action. And he can use that to achieve some goal. And another reference, which I'm not going to dive into, but there is also evidence in neuroscience that the ability to kind of simulate and plan come with some specific brain structure, which are associated with a mammal and some type of bird. So, all of this kind of suggests that, if we want to achieve planning, we need to develop this kind of world model. But maybe let's try to formalize that a bit because world model, sometimes it's a bit abstract. So what do we mean by world model? So simply here in this talk, what I'm going to define as a world model is a model that takes as input some kind of state. So like can be low level perception, might take as input observationally some action. So like put rock into the water. And then it can infer what would be the effect of an action on the state representation. For instance, here I have some observation. I want to say what would happen if I put rock into the water. And if I can do that, I can reach food. And so world model allows an agent to simulate the effect of an action on the environment. And once you have that, the nice thing is you can actually search within your world model using some kind of test and compute to find a set of action to achieve the desired goal. Okay, so now the question is, how do we learn such a world model? And once you start looking into this problem, one thing that appears quite quickly is scarcity of interaction data. So for instance, let's consider this example. So, you have someone on a bike and, internally there's some kind of inner model of where this person is and, what is the different road, what is the different set of action it can do. But you have a lot of state action pair combination. You can move forward, move backward, and this is only one state. And, it can explode quite quickly. Yet, if you look at data available on the internet, you don't have a lot of offline interaction data. And for instance, one reference point, so OpenX embodiment, which is one of the largest robotic data sets, is on the order of 3,000 hours of robotic trajectory and video. But if you consider something actionless, so just only video, you can easily get millions of hours using YouTube or any big available online video sources, right? And so this kind of raises the question of, can we leverage like actionless video to learn a world model that is able to interact with the world in a sample efficient manner? Because again, we don't have a lot of interaction data. And really, this is kind of the core question behind this kind of V-JEPA 2 project. And specifically here, we're going to try to use the self-supervised learning machinery to see if we can make progress onto this question. But maybe before describing our contribution in more detail, I just want to very quickly review some of the existing work. And I'm going to review like three main family of work. So the first type of related work is model-based error. Of course, this is not the first paper to look into world model. There is an extensive literature on it. And one of the notable contributions are model-based error. Here I highlight two work, one from David A. and Jürgen Schmidhuber, so world model. This is a paper that kind of introduces this terminology. And another one is kind of the Dreamer line of work from Hafner and R. And basically, this set of this family of work kind of combines this idea of predictive model in representation space. Usually they use that with a RL framework, so they have to leverage rewards. Sometimes they use policy, and they demonstrate that you can actually solve tasks like a planning task or like locomotion, this type of task in simulator. But maybe one limitation of this line of work is, for training the model, they rely solely on action observation data, which might hinder their scalability beyond simulated environment, right? Because when you are in simulation, you can generate a lot of data this way, but as you want to move towards the real world, then data is going to become scarce, as we saw before. So this is one type of work. Another set of work are generative world model, and I'm sure you've been seeing a lot of generative world model lately. Genius 3 is one of the new models that came out recently. Here I'm showing some illustration from the Cosmos paper from NVIDIA, which was presented earlier this year. And so here the nice thing is, so they're going to learn a world model, and they're going to combine observational data and action-specific data. And usually they have some kind of two-stage training. So first they're going to pre-train a video generative model on observation data only. Here I think they use on the order of 20 million of video hours. And then they're going to have a post-training process where they're going to specialize their model for action-specific type of data. So here, they show that maybe you can unlock and scale training this way. But maybe one of the limitations is most of the evaluation of this type of model focus on the generation quality and is it visually appealing, but they don't necessarily demonstrate that you can use this model to solve actually planning tasks in the real world. So it's more like, okay, you can generate like a good looking plan and they look reasonable, but it's unclear at this point is that if it would transfer to an actual robot. And the last family of work, which is kind of related, are a video foundation model. So this is kind of the background of the team to some extent. So here there is a bunch of work. So on the left, I'm highlighting an illustration from V-JEPA V1, so our previous work. On the right, this is a new paper from DeepMind calling Scaling for the Representation. And so the goal of this family of work is to demonstrate that by using self-supervised learning and large video datasets, you can learn good representation for video. So you can learn good representation of state of the world. And one of the previous results that we show in V-JEPA V1 is, and it's kind of more general to SSL, is you can learn a general backbone this way. So you can pre-train one model and then apply it to a lot of downstream tasks, such as like image classification, action classification, and so on. And the scaling for the paper kind of shows that, with more data and increasing the scale of your model, you can see some kind of scaling law or scaling benefit on some downstream task. Here it's like action recognition with something V2. So you can see as you increase the model size, you get better accuracy or depth estimation. So this kind of validates the fact that you can learn good representation of the world through observation. But this family of work didn't really explore how can you apply this model to unlock like predictive ability and planning ability. And this is kind of the angle we're gonna choose for this work, is like, okay, can we take this SSL machinery and show that we can, solve like planning downstream task? Okay. And so yeah, as I was saying, the question we are asking here is like, can we leverage actionless video and SSL to learn to interact with the world in a sample efficient manner? And basically, we're gonna have some kind of multi-stage process or multi-stage training. First, we're gonna gather a large video data set, which more than 1 million hours, and pre-train like an actionless world model. So the goal of this phase is really to learn a good state representation of the world, right? Then once we have this model, we're gonna have a post-training process where we're gonna leverage a few interaction data, and we're gonna constrain ourselves to use only 62 hours of Joint, because really we want to show the sample efficiency aspect that, with roughly few days video, you can learn an agent that is able to interact with the world. And then once you have this model, we're gonna try to deploy it 0 shot in your environment to solve like actual tasks, like pre-answer mapping manipulation tasks, so grasp or pick and place, this type of thing. So this is kind of the high-level picture of this project. And I'm gonna start by maybe describing this first phase. So how do we learn a good representation of the world by observation? Okay. So basically here we're gonna mostly leverage the recipe that we developed with V-JEPA V1, but we're gonna try to scale it to a larger data set and larger model. And so one of the key hypotheses we are making here is the importance of using a self-supervised learning loss to learn a good representation of the world. Why? Well, first, most of the video data come without an explicit supervision signal. So if you want to scale the amount of data you train on, you need to train without supervision. Then there's the question, is it really important to train on video data? And here we make the hypothesis that common sense information or like low-level motor kind of control information is not something which is easily expressible through text, for instance. And so it's important to have an approach which is kind of grounded in the perceptual input to get this type of knowledge into your model. And the last hypothesis we are kind of putting forward is, the world is messy, the world is not fully predictable. And so you don't want to try to predict everything from the world. And instead, you want to focus only on the bits that are predictable from your data. And this kind of target us to use a discriminative approach rather than a generative approach. And so all this kind of hypothesis motivates the use of a joint embedding approach, and more specifically V-JEPA, so Joint Embedding Predictive Architecture, that I'm going to describe next. So here is how pre-training is working. So we have a video, so an unmasked video, which is kind of a target. And then we're going to apply a corruption operation. So we're going to apply a masking operation and remove some of the patch from the video. Sorry. Okay. So we remove some of the patch of the video. And then the goal is going to try to predict what is the missing content of the video, but not in pixel space, in a learned representation space. So how are we going to do that? we're going to have an encoder that's going to process the masked video and output a representation. And then you're going to have a teacher encoder that's going to process the visible video and output the representation of the visible video. And then we're going to have a predictor whose goal is basically take the representation of the corrected video and try to predict the representation of the uncorrected video. So the predictor is going to take the extra information in the sense of mask token, which is going to specify which location in the video you want to predict. And then we're just going to have a matching loss between the representation of the teacher and the predicted representation, right? Okay, so of course, if you do that, you have some kind of trivial solution. So let's say the predictor, the encoder learns to output a constant vector, and the predictor just copies this constant vector. It's a perfectly valid solution of this system, but it's not super useful. Like, you don't encode any information from your input. So this is what we call a collapse in SSL. And this is one of the main difficulties of this type of approach, is how do you avoid collapse? And the community have developed several ways to avoid collapse. You can use contrastive sample. You can use like dimension contrastive sample like VCREG. Here we're going to use a slightly different approach. So we're going to use a distillation-based approach and an exponential moving average. So what do I mean by that? So when we kind of solve this optimization problem, we're not going to backprop the gradient through the teacher encoder. So we're going to have a stop grad here. And instead, the weight of the teacher encoder is going to be an exponential moving average of the student encoder. And this is kind of a solution that was introduced in a DeepMind paper called BYOL, and has been used like in many SSL approach, such as like DynoV2, V-JEPA, etc. And so the kind of trade-off here is like, usually this type of approach leads to very good empirical performance and very good representation. One of the issues is since we have a stop grad, we don't have access. So what we optimize is kind of a proxy of the loss. We don't have access to the actual loss we are optimizing for. And so, it's a bit of hard to make this type of approach work and require a lot of, experimental struggle. But if you can make it work, usually you end up with very good performance. Okay, so again, this is kind of the recipe of V-JEPA V1. Now, the work we did in this project is trying to scale. And so we're going to try to scale along different axes. First, along the data axis, along the model size axis, and also along the resolution axis and long training. So in this plot, it's kind of a summary plot of the effect of scaling, where we kind of ablate like each intervention. So the first column here is like the V-JEPA V1 baseline. And what we report is average accuracy on a bunch of image and video classification tasks. So here are the tasks. So we have ImageNet, something V2, kinetics, and so on. And it's basically a mix of tasks that require like either motion understanding, meaning that you need to look at several frames to solve the task, or appearance-based understanding. So looking like ImageNet, you only have one images and you have to recognize the object. And so we see basically that by each one of the scaling intervention, we are able to improve the performance. And overall, we see like quite a significant boost over V-JEPA V1 through data scaling, model scaling, long training. So we train for more iteration. And also we have like a high resolution annealing phase where we kind of upsample both the spatial and the video duration, which help quite a bit to improve the performance. I'm not going to go too much into the detail in the interest of time, but I just want to highlight one thing about the data. What is important also to realize is data scaling is not just training on more data, but it's actually curate the larger scale data set and build on a data set with an interesting distribution. And you can see this plot on the right. So in this paper, we use a curation process, which is kind of the video extension of the DynoV2 curation process, where basically we're going to start from a very large pool of data. So it's a YouTube video from the YouTube temporal 1B dataset. And then we're gonna have some retrieval process to retrieve videos that are kind of similar to a target distribution. And the target distribution is basically the set of downstream tasks we are interested in. So at a very high level, we embed all the video into a representation space using Dino V2. Then we're gonna have a clustering process, and we're gonna only consider cluster whose video are similar to the one of the target distribution. And so here you can see the effect of data curation. So basically, it allows you to kind of increase across the board and for all of the tasks the result. And I'm not showing that in this part, but if you don't do this curation process, sometimes you don't see the benefit of data scaling. So it's very an important part of the recipe. Okay.
Awesome. Nicolas, you want to do a small break to answer some of the
Sure.
of the questions in chat? Okay. I see a question from Stepan. So, Stepan, if you want to go ahead and ask your question.
Yeah, sure. Thank you so much. I just excuse me. I just had some confusion looking at I-JEPA and V-JEPA papers and looking at the repo and Hugging Face. So I posted my question there if you'd like to read it yourself. But during inference, is the context encoder and predictor that are being used to generate the embeddings, or is it the target encoder? And the reason why I'm asking is because the source code in the V-JEPA repo and I-JEPA paper seem to point to the target encoder, but the V-JEPA paper and blog post point to the context encoder and predictor. So I was just a little confused between those two.
Yeah, so for downstream tasks, we tend to use the target encoder because it's like a moving average of the context encoder. And usually you get a few more points, but it's not like a huge change. Maybe you get 1 point, 2 point better on the downstream task. But yeah.
Awesome, thank you so much. And that's for all the JEPA architectures, right?
Yes, most of the time.
Thank you.
Awesome. Okay, we can answer one more. Chen Kunli, if you want to ask your question, please go for it.
Hi. Thanks for the presentation. It's a really good work. I'm sorry, I'm on a train, so the connection problem is a bit bad. How sure are we on this paradigm, like by scaling the model and the data? Well, do these in the end lead us to train a data-driven model that's accurate to capture the physics? And if this is the ultimate goal, are there other alternatives?
Yes, so we actually have another work where we kind of delve into the physics understanding and intuitive physics understanding on the V-JEPA 1 model. And in this work, we kind of show that you actually don't need a lot of data to get this understanding. And what I mean by intuitive physics is property like object permanence, or that things should not appear out of nowhere, gravity and things like that. So it seems that you can learn to understand those concepts in a data efficient way. For more semantic downstream tasks, like if you look at classification, for instance, and if you want to have like a broad coverage of tasks, then I would say scaling is important. Also, it's still relatively low scale compared to what they do in LLM side of things. So I think we still have some work to do there.
Thanks.
Awesome. Thank you, Chankun. Great question. We have a couple more. We'll save those for the end. Also, everyone else, please feel free to leave your questions in the Q&A section down in the Zoom bar. You're gonna see that option. And at the end of the talk, we'll have a decent amount of time to have a more open Q&A. Nicolas will answer all of these. So yeah, please feel free to leave all your questions there.
Thanks. Okay, so this is So this was kind of how we do the pre-training with observation data. But then there is a question of how do we validate the model? Because since we do everything in representation space, we cannot compute easily like a likelihood metric on your data distribution. So you need to define a set of proxy tasks to assess the quality of your model. So in this work, we look at two sets of proxy tasks. One is through language alignment. So basically, we take our video backbone and align it with a LLM, and then solve tasks related to video QA and see, can we get good performance this way? And the nice thing about language alignment is, it provides an open-ended way to test your model, and you can test like a variety of concepts quite easily. The other framework we are using is like attentive probing. So basically, we're going to take our backbone, we're going to froze it, and train like a classification probe on top of it with some kind of attention architecture. And this is kind of the result I was showing before. And then we can train different probe for different type of tasks, so action classification, object recognition, and so on. And I'm just going to show a few results there, just to kind of show you that and validate that the backbone we learned can represent the world with a nice property. So first, we're going to look into the alignment of V-JEPA 2 encoder with the LLM. And the first thing we did is kind of a control experiment where we're going to take a LLM. So here we use the Qwen2 7B model and take a bunch of state-of-the-art visual representation backbones. So we consider like DynoV2, SIGLIP, and the perception encoder, which is like a clip type encoder recently released by Meta, by FAIR. And so we're going to be in a frozen backbone setup. So we're not going to train the vision part and just train and align the vision part with the LLM. And we're going to use the same set of alignment data and then look at the performance across various tasks. And we kind of select tasks where either you need some kind of physical understanding of the world. So it's like the perception test and MVP, or like a temporal understanding of the world. So time compass, temporal bench, TV bench are more like that. MV bench, usually it's more correlated with appearance understanding, and we also kind of track it just to compare our model with the other backbone. And so what we see here is that in this controlled setup, again, we can get quite competitive performance compared to other backbone. And I think it's an interesting result because before in the VLM community, there was this idea that you need to have a vision backbone which is aligned with language in order to unlock good performance with a LLM above. And what we show here is that actually you don't need any text supervision when you pre-train your vision part. Even with a SSL pre-training, you can get competitive results. So this is a control setup. You can also do a system level comparison. So here we just take the best number of each approach from their paper. And we also train our model. So here everything is trained. We have fine-tuning of the visual backbone. And it's not like an apple-to-apple comparison because everyone uses different training data sets. They might not use the same LLM. But the goal of this comparison is to show that, okay, even with our approach, you can get a competitive performance and achieve like a state-of-the-art result on some of the data sets. So showing that you learn a good representation of the world. I'm going to skip the post-based evaluation in the interest of time. And so the result I showed before focus on understanding what you see. We also have evaluation that try to probe if the model can understand what's going to happen next. So understand the predicting capability of the model. And here we focus on the Epic Kitchen dataset. So it's like an egocentric video of people doing singing in a kitchen. And basically here, each time the video pause, the model has to predict what will happen 1 second into the future. And to do that, we're going to leverage our predictor. So basically, we're going to use a predictor to predict the representation of what will happen 1 second into the future, and then decode it back into like an action space with an attentive probe. And our predictor and encoder are frozen. We only trapped a small probe on top of it. And we can see here that our model is actually quite competitive. And it's kind of a narrow evaluation because it's only focused on cooking, kitchen stuff. But in this setup, we can get a pretty good performance at inferring what will happen 1 second into the future. We did try to push that a bit, like what will happen 5 seconds into the future, 10 seconds into the future, and we do see quite a rapid degradation of performance. So it's something we need to improve moving on. Okay, so that was kind of the first phase, learning by observation. Again, the goal here is to take a big pre-training data set and learn a good representation of the world by training an actionless world model. Now, that's only part of the picture. And the next thing we want to do is a post-training process where the model learns to infer what is the effect of action on real-world interaction data. And so here we're going to focus on the Droid dataset. So it's a dataset of a Franca robot performing some kind of robotic manipulation, object manipulation. And we're going to have this kind of post-training process. So what we're going to do here, it's kind of a similar framework. So we're going to have a video. Here we don't have any masking of the video. So we're going to see the full video in the encoder. And we're going to try to predict the representation of the future frame of the video. So it's actually a causal prediction task. So given the past, trying to infer what's going to happen next in the video. And so we're going to keep the encoders that we pre-train from the previous step, but we're going to train a new predictor. So this predictor starts from scratch, which is conditioned on the past frame and on the robot state and action. So, you know what is the current state of the robot, and you know what is the action that the robot's going to take. It's going to try to predict the representation of the future frame and match it with the actual observation. And one important detail here is we kind of froze the encoder. So basically, since we are kind of in a data constraint regime, we don't want to use that to learn a representation, but just focus on the predictive ability and learn a predictive model here. So to explain a bit more in detail the training process, so we're going to combine two loss. One, which is kind of a teacher force loss. So basically, we have input sequences. We're going to use our V-JEPA encoder to extract frame representation. One thing here is like we actually encode the video as a set of frames. So we apply the encoder only on one image at a time, not on the full video. And it's something we're going to change at some point. Then we're going to interleave the representation of the frame with the robot state and action, and then try to predict what would be the future state, future representation, future frame representation of the robot. And yeah, this is kind of teacher forcing. So we're going to always see the full ground truth history and only try to predict the next step. So if you do that, you can get a model that is working, but you also see a lot of accumulation of error when you do like a rollout. So when you feedback the prediction, and so to fix it or to mitigate this a bit, we also have like a rollout loss, where basically we're not gonna feedback the ground truth observation, but we're gonna provide the previous prediction. So here you see the first frame, you interleave with robot state and action, you predict what would be the representation of the next frame, and you feed that back to your predictor. So it's kind of, you do a rollout. And after a few steps, you're going to try to match your predicted state with the actual ground truth. And so this is, again, it's just to mitigate the error accumulation you might have in your model if you only do like a teacher forcing loss. Okay, so yeah, this is, maybe if there is any question before I present the planning results regarding the post-training phase.
I think maybe it would be better for you to go to that, and then at the end we just do like a full-on Q&A, so it's a bit more fluid.
Okay, sounds good. So now that we have so after this post-training, we have a model which is able to infer what would be the effect of an action on representation of the world, and so we can try to deploy it zero shot on a robot using planning. So how are we going to do the planning? So basically, we're going to use model-based control, which is something odd approach, and the idea here, and we're going to use more specifically the cross-entropy method to search for the set of action to achieve a goal. So we have like an initial frame that we're going to encode, and then we're going to sample randomly a sequence of action that's going to going to encode randomly a sequence of action and then predict what would be the representation of the video if we apply this sequence of action On the other side, we have a goal images, which is the goal we want to reach. We're gonna also get this representation, and we're gonna have a loss between the representation of the goal and the representation of the predicted outcome. And basically, we're gonna try to minimize this loss by optimizing over the action. So we're gonna try to find the set of action that minimize the prediction between what we think will be the state where we're gonna be and our goal. And how we do this minimization is a cross-entropy method. So basically, it's akin to random search, right? So we just gonna sample some action according to a Gaussian distribution, evaluate the cost, only retain the top K action, and update our Gaussian parameters this way. Sorry, I'm going a bit fast, but this is kind of the whole pipeline. So we have a start frame and a go frame. Then we're gonna unroll our one model, so to kind of predict what is the effect of different action. And we are gonna compute a cost for each one of those trajectory. Then we're gonna pick the ones that minimize our cost, and we can do execution on the robot after that. And this is closed loop planning, meaning that each time we do an action, we're gonna do this planning process. Okay, so maybe let me skip that and focus only on the pick and place results. So we evaluate on different tasks, so reach, grasp, and place, and pick and place. And for pick and place, because our current model is not able to do non-greedy planning, we're going to provide sub goal. So we're going to provide like the grasping goal, the kind of a goal where you need to move the object, and then when it's going to release the object, and then we're going to provide that to the system with the initial frame, and the robot has to find the set of action to actually satisfy all those constraints. And this is actually what the robot is seeing. And this is actual execution on the robot. So you can see that you can go down to the cup, grasp the cup, lift it up, and then is able to release it on the shelf. And again, I think the set of results, they are not without limitation, but they are quite exciting because it's zero shot. We don't train on this environment. It's with new objects that were not seen during training. We don't have any camerized transit, so the robot has to infer the coordinate axis the model has to infer the coordinate axis of the robot, and it's solely trained from unlabeled signals, so we don't have any supervision anywhere. So this is in the Montreal lab. We also try in a different lab in Menlo Park, and again, we don't have any training data from this lab in our training data sets in this different type of object, and is able to do this task successfully. Okay, so this is some qualitative results. We also have quantitative results. So here we compare with two sets of baselines. The first one is Octo, which is a VLA type baseline, imitation-based learning. We choose Octo because it's one of the VLAs that can use image co-conditioning. Most of the other VLA require a language goal. So to have more apple-to-apple comparison, we focus on Octo for now. And so we take this model, we fine-tune it on Droid, so they're fine-tuned on the same type of same Droid data set. Octo is trained on more robotic data also. And then we try to deploy both approach zero shot for the different tasks, so reach, grasp, reach with the object, and pick and place. And you can see that, if you look at reach, both models perform well, but as soon as you have like object manipulation, preemptive manipulation task, we do see a huge improvement by using a one model-based approach in that setup, in that comparison. But you can also see that our success rate is not perfect, right? So it's like a good, it's a good gradient, let's say, but we still have some work to do to make it work more reliably. But yeah, again, this is the first one model to showcase the ability to perform preemptive manipulation task zero shot without task-specific training reward or camera specific. We also compare with a generative approach. So this is the Cosmo model from NVIDIA. And so here we're going to use the same model-based control protocol to compare the two approaches. One thing is, so here's the number of sample we do rollout on, like the number of action we execute to see what is the effect of action. And already you see that approach that kind of more biased toward generation. It's not as practical to make that work on the robot because just generating a video takes a lot of time. And so basically, if you want to run a pick and place experiment, it was taking on the order of hours just to search over the action space. So kind of limits the amount of experiment you can do with that. While if you do the prediction representation space, is way more efficient. And so here you can see that our approach is compared favorably compared to Cosmos. And Cosmos works very well, for pose matching type of task. But actually, object interactions still seem to be a challenge for this type of generative approach. Doesn't mean that it's not always going to be a challenge, but it's one of the limitations we have right now. Okay, of course, our current model is far from perfect. Few limitations we have. So first, the current approach requires long image goal, which is not very realistic. When you want to achieve a goal, you don't have an image of the goals that you want to achieve. So eventually, we will need to move toward like a language-based goal. Second thing is long horizon planning. So even with this kind of rollout loss, we do see a bit of error accumulation, most likely because we train on very few data, this new predictor. And so this kind of limits the range, like the time horizon at which we can do planning for, and that's why we need the sub-goal. But it's something that probably it will be quite manageable to remove. And the last thing is sensitivity to camera positioning. So in the set of results, we always have the kind of same camera position when we execute on the robot. And we do observe that if we move the camera, the performance can sometimes drop. And it's because, it's because of two reasons. One, again, we don't use a lot of training data, so we don't have a lot of data to infer the coordinate axis of the robot. And also it's kind of, it's not a well-defined problem. If you have only a single view, you have potential different solutions that is valid. So the model has to take its best guess. Okay, so conclusion. So in this work, we show that using SSL and large-scale video data, we can build a model that understands physical world and is able to plan, understand, and predict. So the main ingredient is scaling action-free SSL on video data, then post-training the model on a small robotic data set to understand what is the effect of action, and then deploy it zero shot on a robot. So yeah, that's it for me. Thank you.
Awesome. Thank you very much for the talk. I'm sure there are a lot of questions, so let's move forward to that. Sean, do you want to go ahead and ask your question?
Sure. Thanks for your presentation. Most of the examples you showed are traditional, real world examples like a dog running, bike playing. Have you applied this to anything scientific and potentially on like microscopic scale? So like cells dividing, neurons searching for connections, crystals forming, that type of stuff, and being able to sort of leverage it more for science predictions as opposed to a much larger world model. So like a much smaller world model with more constraints.
Right. So we didn't do that directly, but I can point you to two work. So there is a recent work from DeepMind that tried to leverage this type of approach for more like a scientific application, and that look in particular into microscopic images and show that basically you can get reasonable performance using so it was with the V-JEPA V1 approach. So it seems that you can see some transfer, and there is also work that basically don't take the pre-trained model, but try to take the training formalism and apply that to their own data. And it seems quite reasonable too. I don't remember the paper by name, but it's something that has been explored by the community, not by us.
Gotcha. Thank you. And the first one was DeepMind, you said?
Yeah. I think Pauline Luc is one of the authors, but I don't remember the paper name.
No, I can Google. Thanks so much.
Great. Thank you so much, Sean. Howran, I see you have a couple questions. Do you want to go ahead and ask him maybe one at a time so that Nicola can answer them progressively?
Yes. Thank you so much. Thank you, Nicolas, for the great talk, and thank you, Santi and John, for the coordination. I do have several questions. So, the first question is about the pre-training loss. And as many people reported on the GitHub, when they reproduce the V-JEPA and V-JEPA2, they observe that the pre-training loss firstly decrease, and then increase, and then decrease. So this phenomenon makes us harder to quantify when we should stop the pre-training. So could you help us understand better about this phenomenon?
Yeah. So the main reason for that is, again, the stop gradient, because once you have a stop gradient, you don't, so we have a loss, but it's just a proxy loss. This is not the object we optimize for. And so that's why we have this kind of weird loss curve, because we don't have access to the true loss. So it's true that if you look at the JEPA loss, you're going to see that it's first going to drop, then it's going to go up again, and then it's going to, saturate and go down quite slowly. The way we do to kind of assess the model capability through training is, we just every, X iteration, we're just going to run a bit of downstream task evaluation and see what is the score. It's the only way we have right now to kind of assess if the model is still learning something interesting or not. So unfortunately, it's quite a complicated process. And one of the things we are kind of investigating next is, can we get a proper loss when we do this pre-training? So can we have a loss without a stop grade, which would allow us to, have proper loss curve and also track the performance of the validation set.
Thank you so much. And for the downstream task, if you choose to fine tune for the downstream task, it's time consuming. But there are some simple tasks like KNN classifications. But as people also reported on GitHub, when they do the using the pre-trained representations for KNNs, or using the PCA for realized features, they sometimes look worse compared with Dino V2. Is it because V-JEPA is focusing on high-level nonlinear representations, so that k-nearest neighbors and PCA fails in this setting?
Yeah, so the Dino V2 type of loss, you do have some kind of cosine similarity that you compute with a set of prototype. And this does help quite a bit to improve the nearest neighbor retrieval performance, because basically the task you optimize for is more akin to nearest neighbor, right? You want to retrieve a set of prototypes that are similar to your current patch, etc. So we don't have that in V-JEPA 2, because what we want to focus on is more on the attentive probing type of performance. So basically, you just fit a small attentive probe on top of your representation to get a classification score.
Okay. And another question is that so V-JEPA and so the JEPA series is a joint embedding predictive architecture, where traditionally the embedding is defined as adding is a representation after some projector layers. So my question is that, have you tried to introduce the projector into V-JEPA 2? And if you try to introduce, should the projector be applied for each patch representations, or should it be applied to the average of all patch representations?
So it's not something we've been exploring. My guess is, if you want to have this type of solution, you should apply it on each patch representation, because when you take the average, you're going to lose a lot of information, right? So okay. I think it would make more sense to have a projector which is applied on every patch. It might be a computational projector as well, where you apply it on a bunch of patches at the same time. Yeah, but we don't have any empirical results on that.
Okay. And
awesome. Thank you. Maybe
can we have one more question? Sorry about that.
No, go for it. I was just gonna say, maybe we can move to someone else to ask a bit more questions because we're running a bit out of time. So,
Okay.
but if you have like a direct follow-up, please go for it.
Okay, just a simple question, and then I will finish. Maybe a stupid question, like when in self-supervised learning, like is there a difference about representation, latent, or embeddings? Is it just a notation difference?
It's the
or
same thing, yeah. It's
Okay.
just different community use different term. Yeah.
Okay, thank you so much. That's all my questions. Thank you, Sandy and John.
Awesome. Thanks so much, Harlan, for all the questions. Really, really insightful. Shantanu, good to see you again. Do you wanna ask your question?
Yes, happy to say, hey, Nicholas, thanks for the talk. I think so. One of the things I wanted to highlight was that, biomolecular phase modeling has been extensively studied using some of the energy landscape models, like the work from Peter Wallen's lab or Walsh's lab. Do you foresee, like, from just purely from a research, forward-looking research perspective, do you foresee like being able to have like a sidecar where we are doing just-in-time simulation of, the trajectory, the planned robotic action? And then based on whether the simulation suggests, something else, yay or nay, right? Like based on that, we go with the original plan, but then, that's like an additional validator whether to proceed ahead or not. Like, so those APIs I haven't seen as much. Curious to hear your thoughts on that, broadly.
So I'm not sure I fully understand your question. Let me rephrase it maybe. So like you are asking if we use a simulator to validate the plan, can we use that to improve the planning capability?
Yeah, so there is one trajectory which is like, where the plan is automatically going, but concurrently, like we run sidecar simulations as well
Right.
to validate if there are any errors, and and then
So-
based on that we intercept, so, yeah.
Yeah. So it's what we are trying to. I mean, it's like a small step in that direction with this project. So basically, we have like a simple constraint getting to a goal, and then we try to find a set of actions for the optimization process to get to this constraint. But you could have more constraint. Like you could have like a different type of loss. You might hardcode some of that if you have some kind of specific requirement. You might want to have a set of actions that minimize the amount of energy that your agent take or things like that. And because it's just set up as an optimization process, it's kind of easy to add a constraint, remove a constraint, and explore that. And the optimization process, everything happens in parallel, right? So, and again, it's closed loop optimization. So, each time you take an action, you're going to start running this optimization process again.
Awesome. We probably have time for 2 more questions, if that's okay with you, Nicola.
Yeah.
Awesome.
Sorry, I took a lot of time.
No, it was perfect. No, that was great. Doug, do you want to go ahead with your question?
Sure. I was wondering if there's any work to kind of fine tune the V-JEPA model in, say, like a robot simulation environment, since there's probably existing environments that that might help in terms of actually like nailing down the exact actions.
Yes. So we actually had this debate in the team, like should we focus on simulation or not? And it's kind of when we were discussing with robotic people, they were saying that simulation is useful because it allows you to filter model. Like if it doesn't work on simulation, it's not going to work on the real robot. But it's not enough. Like sometimes you have a good model in simulation, it's not going to transfer well on the real robot. So that's why we kind of decided to just try on the robot directly. The issue with the robot is, running experiment takes time. Like you have a new bottleneck, you have the robot time bottleneck. So having a simulation to kind of do a bit of exploration around that, it kind of makes sense. But we don't have any model trained on simulator right now.
Great. And then are there any approaches for kind of continual learning on the deployed robot afterward?
No, but it's something that would be interesting actually.
Thank you.
Awesome. Yeah, we can ask. We can go with one more, and maybe depending on time we can see. Stepan, I see you have a couple more questions. Do you want to go for them?
Yeah, for sure. Sorry, I had the question on the V-JEPA actually, and the differences between that and V-JEPA. Well, first question, is the robot moving in real time, right? In those videos, it's pretty amazing that it can replan so fast, just given the like sheer amount of possibilities, right? With every replanning step it has to do. And the second question about the V-JEPA is the high level versus low level forecast. Why wasn't that sort of used in V-JEPA, and whether the architecture itself is good enough for long-term planning, in your opinion, that the two levels in V-JEPA are not necessary?
Yeah. So for the first question, let me go back here. So yeah, basically, for each time step for planning, for each planning task step, right now it kind of require like on the order of 10 to 16 seconds. So it's not real time, but also it's not something we optimize for. We are not using like a very powerful GPU on the robot, so it's definitely something we could manage to achieve. So it's not real time, but I don't see any strong bottleneck to make it this way faster. On the second question, so actually, yeah, we didn't explore the hierarchical component because you want to explore one thing at a time and don't add too much complexity. But definitely, it's something we are seeing right now. Is once you have a hierarchical model, all of a sudden you are way better at long range prediction, and you can start tackling longer horizon planning tasks. So yeah, we don't have result to communicate yet, but it seems a promising direction.
Thank you so much. The reason why I ask is because modern LLMs in robotics have exactly that sort of two levels of planning.
Yeah.
Awesome. Well, Nicolas, there are only two more questions. If you